Hello, Matt here from chemistrystudent.com. In this video, we're going to look at the equilibrium constant, Kp. We're going to talk about what Kp actually is, mole fractions and partial pressures, and how to calculate Kp and its units. Equilibrium, Le Chatelier's principle, and the equilibrium constant Kc have been covered in separate videos. Check the links in the description below. Before we talk in detail about Kp, there are a few essential ideas you need to be comfortable with. A reversible reaction is one in which the reaction can proceed in both directions. Reactants can react to form products in what is called the forward reaction, and these products can also react to form the reactants in what is called the backwards or reverse reaction. In a closed system, reversible reactions reach dynamic equilibrium when the rates of the forward and reverse reactions are the same, meaning concentrations of all reactants and products are constant. Positions of equilibrium describe how the concentrations of products and reactants compare to each other in an equilibrium mixture. If there is a higher concentration of products compared to the reactants, the position of equilibrium is said to lie to the right. If there is a higher concentration of reactants compared to the products, position of equilibrium is said to lie to the left. Gas pressure refers to the force exerted by gas particles on the walls of a container. The more particles there are in a given volume, the greater the pressure, as there are more particles hitting the walls every second, meaning a greater force is exerted overall. Fewer particles in a given volume mean a lesser pressure. A homogeneous system is one in which all the reactants and products are in the same state. Recap done? Let's go! When dealing with systems that are at equilibrium, if we want to know an exact position of equilibrium, we need to compare the amounts of products to reactants in the mixture. To do this, we divide the concentrations of products in the mixture by the concentrations of reactants. The value obtained is referred to as an equilibrium constant, represented with a capital K. There are several different types of equilibrium constant, but the most general one used is based on molar concentrations, mole per decimeter cubed, and is called Kc. For gas-based systems, however, we can also think about the amounts of products and reactants in terms of their partial pressures in the system, given a different type of equilibrium constant called Kp. In a mixture of gases, the total pressure of the system is made up of the partial pressures of each gas type in the system. You can kind of think of it as each gas contributes to the overall pressure of the system, and their individual contribution is called its partial pressure. For example, imagine a sealed box with two gases in, A and B. The gas pressure inside the box is 100 kilopascals, and there is 1 mole's worth of A and 1 mole's worth of B inside the box. This means there are 2 moles of gas particles in total, causing an overall pressure of 100 kilopascals. Each type of gas, therefore, can be considered as contributing 50 kilopascals of pressure to the total pressure of 100 kilopascals. As 100 kilopascals divided by 2 moles gives 50 kilopascals per mole of gas. There is 1 mole of A, meaning 50 kilopascals of pressure comes from gas A, and there is 1 mole of B, meaning 50 kilopascals of pressure comes from gas B. These pressures are called partial pressures, and in this case, the partial pressure of gas A is 50 kilopascals, and the partial pressure of gas B is also 50 kilopascals. The total pressure in the box equals the partial pressures of all gases in the box added together. In a closed homogeneous system, all gases are at the same temperature and in the same volume, meaning it is the number of moles of each gas type that determines their partial pressures. This means then that the ratio of partial pressures of gases in a system is the same as the ratio of moles of those gases in the system, Sounds a bit confusing, I know. Let's imagine that sealed box again, this time with a total pressure of 150 kilopascals and 2 moles of gas A and 1 mole of gas B inside. Now, to figure out the partial pressures of A and B, we first need to know how many moles of gas there are in total inside the box. 2 moles of gas A and 1 mole of gas B means there are 3 moles of gas inside. Of this 3 moles, 2 moles are gas A. That means 2/3 of the gas in the system is made up of gas A. This is called the mole fraction of A, and is the ratio of moles of A in the system compared to all other gases. It is calculated by dividing the moles of gas A by the total moles of gas in the system. The mole fraction of gas B would be 1/3, as there is 1 mole of gas B and 3 moles of gas in total. If the total pressure of gas in the box is 150 kilopascals and the mole fraction of A is 2/3, that means the partial pressure of gas A must be 2/3 of 150 kilopascals. In other words, 2/3 times by 150, giving a partial pressure of 100 kilopascals. Equally, the partial pressure of gas B would be 1/3 times by 150, giving 50 kilopascals. The partial pressure of a gas then is its mole fraction times by the total pressure of the system. We can check if these values for A and B here seem right by adding them both together. They should equal the total pressure of the system. 100 plus 50 equals 150, the total pressure. Partial pressures of all gases in a system should always add up together to the same value as the total pressure of the system. How does any of this link to equilibrium constants then? Well, for calculating equilibrium constants, it is the ratio of product to reactants that is relevant. Based on what we've just said, the partial pressures of gases in a system are based on the ratio of moles of each gas to one another, their mole fractions. This means we can actually calculate an equilibrium constant for gas systems using the partial pressures of the gases present. The constant calculated is called Kp. The little p refers to pressure and the K the fact it's an equilibrium constant. For example, the gases nitrogen, N2, hydrogen, H2, and ammonia, NH3, can form an equilibrium system in a sealed container. To determine the position of equilibrium and find Kp, we take the partial pressure of ammonia and divide it by the partial pressure of nitrogen times the partial pressure of hydrogen. Just like for other equilibrium constants, such as Kc, we have to raise the partial pressures to the power of the mole ratios in the reaction equation. Here, the molar ratio of nitrogen to hydrogen to ammonia is 1:3:2. Meaning the nitrogen partial pressure needs to be raised to the power 1, hydrogen to the power 3, and ammonia to the power 2, giving a Kp expression of Kp equals partial pressure of NH3 to the power 2 divided by partial pressure of N2 times partial pressure of H2 to the power 3. For homogeneous gas-based systems then, we can determine positions of equilibrium using partial pressures of gases in the equilibrium mixture, rather than using concentration. Kp works in the same way as Kc, just using partial pressures rather than concentration. Just like Kc, Kp changes with temperature, and a Kp value for a system is only for a specific temperature. The units of Kp can be different for different reactions, depending on the molar ratios of reactants and products in the reaction equation. Partial pressures have the units of pascals, Pa. To determine the units for Kp, we substitute in the units Pa into the expression instead of partial pressure values, and see what we are left with after the PAs on the top of the fraction are cancelled out by the PAs on the bottom of the fraction. For example, The Kp expression for nitrogen, hydrogen and ammonia we've already seen is Kp equals partial pressure of ammonia squared divided by the partial pressure of nitrogen times partial pressure of hydrogen to the power 3. Well, if we put in Pascal units into the expression, we end up with Kp equals Pa squared divided by Pa times Pa to the power 3. Expanding this out gives us Kp equals Pa times Pa divided by Pa times Pa times Pa times Pa, as Pa to the power 3 is the same as Pa times Pa times Pa, and Pa squared is the same as Pa times Pa. Now we just need to cancel out all the PAs on the top and bottom of the fraction. There are 2 PAs on the top of the fraction that can be cancelled out by 2 on the bottom of the fraction, leaving 2 on the bottom. This now becomes 1 divided by Pa times Pa, or 1 divided by Pa squared. That is the same as writing Pa to the power minus 2, meaning the units for Kp for this expression are Pa to the power minus 2. Sometimes there may be no unit. For example, Kp for hydrogen plus iodine to form hydrogen iodide has no units. The expression for Kp equals partial pressure of hydrogen iodide squared divided by the partial pressure of hydrogen times the partial pressure of iodine. Substitute Pa into the expression again and we have Pa squared divided by Pa times Pa. In other words, Pa times Pa divided by Pa times Pa. The 2 PAs on the top of the fraction are cancelled by the 2 PAs on the bottom of the fraction, meaning no units are left at the end. So, to summarise, Kp is an equilibrium constant that can be applied to homogeneous gas equilibrium systems. Unlike Kc that uses concentrations of products and reactants, Kp uses their partial pressures. The partial pressure of a gas in a system is the contribution it makes to the total pressure of the system. The partial pressures of gases in a mixture are based on the number of moles of each. The mole fraction of a gas is the number of moles of it in a system compared to the total number of all moles of gas in the system. Partial pressure of a gas equals its mole fraction times by total pressure. Kp is calculated by taking the partial pressures of products divided by the partial pressures of reactants, raised to the powers of their molar ratios in the reaction equation. Units of Kp can be different for different reactions. Values of Kp are specific to a particular temperature. If the temperature of a system changes, the value for Kp will change as well. I hope you found this video useful. Please check out other relevant videos in the links given in the description below and visit chemistrystudent.com for free notes and revision materials.